Next interest that we want to do very carefully is the energy of an ideal Bose gas and therefore the specific heat. Our interest essentially lies in evaluating the energy of the ideal Bose gas because we have then a direct route to access the specific heat, which is actually the measurable quantity in the experiment. Now, I know that for a non-relativistic gas, 2/3 of the energy density is equal to the pressure. So therefore, U is going to be 3/2 times PV. And PV, we just now saw, was kBT ln Q plus. So that I have 3/2 of times kBT times G V over lambda T F plus 5/2 set. Again, we ignored the second term in ln Q plus because we are working in a thermodynamic limit, and just as in the pressure we saw that this is going to be, I can ignore that. We will also ignore it in the internal energy, right? Good. For T less than Tc, this quantity Z is equal to 1. So that U becomes 3/2 kBT GV over lambda T times zeta of 5/2. Correct? Good. So I want to calculate the specific heat now. So we will do it in this reduced form. We will write down Cb over NKB, which is going to be d dt of U over NKB del T of U over NKB and that is G 3/2 GV times KB times zeta 5/2 times del T of T over lambda T. Correct? Okay. So this is, let's see how can we do it very easily. Now, lambda T is alpha T to the power minus 3/2. Right? So that T over lambda T is going to be alpha times T to the power 5/2, and therefore del T of T over lambda T is going to be alpha del T of T to the power 5/2, which is 5/2 times alpha T to the power 3/2. Can we express it in terms of this? I'm sorry, this is my mistake. So this has to be T to the power by alpha. So that this is 1 over alpha and this is by alpha, which is 5/2 alpha T to the power minus 3/2, and you have 5/2 lambda 1 by lambda T. So that Cv over NKB is 3/2 my mistake, there has to be an NKB over here which follows from this and which I have missed. So be careful with the calculations. So I have GV over N the kb and the kb cancels out, and this I should have been more attentive to. And then I have zeta 5 by 2, and this derivative is essentially this, so that I have 5 by 2 1 over lambda t, so that I have 15 by 4 zeta 5 by 2 gv over n lambda t, and this therefore goes as t to the power 3/2 for t less than Tc. Now exactly at the critical temperature, T is equal to Tc, I have Cv over Nkb is going to be 15 by 4 zeta 5 by 2 Gv over n lambda Tc. But I know that n lambda Tc over Gv is equal to zeta of 3/2, because this is the criteria for obtaining the critical temperature T of C. So I will replace this then as 15 by 4 zeta 5 by 2 divided by zeta of 3 by 2 as Cv over Nkb, and this is the value that you get at T is equal to Tc. Of course, what is left now is to look at what happens to the specific heat for T greater than Tc. The second case to study is for T greater than Tc. And we start off with the usual expression that U is going to be 3 by 2 kBT times PV, and therefore that is GV over lambda T F plus 5 by 2 Z. Now here again I have to determine the fugacity from the total particle number, which I had GV over n lambda T F plus 3 by 2 of Z, so that U over Nkb is going to be 3 by 2 kBT divided by Nkb times Gv over lambda T is n Gv over lambda T. I use this relation to write down Gv over lambda T as n over F plus 3 by 2Z. I can of course determine the fugacity again and then replace it over here, but it is not necessary to do in this analysis. One can do it more elegantly. So F plus 3 by 2Z times F plus 5 by 2Z. Lot of things cancel out, kb cancels out, n cancels out, and I have U over Nkb is going to be 3 by 2 T F plus 5 by 2Z divided by F plus 3 by 2Z. Therefore, the specific heat now becomes Cv over Nkb is del del T of U over Nkb, which is del del T of T over F plus 5 by 2Z divided by F plus 3 by 2Z. Now again, one has to be careful here. Please just don't take a derivative of temperature and be done away with, because that is just only one contribution. You should also note that Z is e to the power beta mu, and therefore that is a function of temperature. But these functions F plus that is written over here are complicated functions. There are no representation of these functions. These are integrals essentially, and you cannot represent them in terms of simple functions. So carrying the derivative is little bit more subtle, but our purpose is to do that. Let's just evaluate the trivial term. The trivial term is the derivative of the first term, that is del del t of t, and you are left out with f plus 5 by 2z divided by f plus 3 by 2 of z. And then you have 3 by 2t. The derivative gives you f plus 3 by 2 whole square of z, f plus 3 by 2 z, f dash of 5 by 2z minus f of 5 by 2. So there's a plus z f dash of 3 by 2 z. This is the complication. So where f dash plus is identical to df dt. Now, the first thing to evaluate these derivatives. How can I do this? How do I evaluate such quantities? For that, we note fm plus of z is integral 0 to infinity 1 over m minus 1. So we go back to the original expression for these functions, dx x to the power m minus 1 z inverse e to the power x minus 1. So that now if I take a derivative with respect to z, this means fm plus z is 1 over m minus 1 factorial 0 to infinity dx x to the power m minus 1 ddz of 1 over z inverse e to the power x minus 1. Let's do this. I mean, there is a simple way of doing it, but I want to illustrate this. So ddz of 1 over z inverse e to the power x minus 1 is going to be 1 over z inverse e to the power x minus 1 whole square, and then I have ddz of z inverse e to the power x. So ddz of z inverse e to the power x minus 1, which is 1 over z inverse e to the power x minus 1 whole square. I have e to the power x ddz of 1 by z, which gives me minus z square. So that this derivative I have minus 1 over z inverse e to the power x minus 1 e to the power x over z square. Okay, what do we do next? Well, we want to convert this, the derivative with respect to z, to a derivative with respect to x. For that, we also note that if I just do ddx of 1 over z inverse e to the power x minus 1, I will come up with not some, sorry, this is a whole square over here, something which is different, but something which is very similar. This, and then I have ddx of z inverse e to the power x minus 1, which gives me 1 over z inverse e to the power x minus 1 whole square times e to the power x over z. So by looking at this that we have evaluated, and then I look at this expression, I can see that I can write down this as this, and then I can write down the rest of it as z inverse e to the power x minus 1 whole square e to the power x by z. But surprisingly, this quantity is this, which in turn is this. So therefore, I have ddz of 1 over z inverse e to the power x minus 1 is minus 1 by z of ddx of 1 over z inverse e to the power x minus 1. Now this you could have easily guessed if you considered that if I have a function, let's say a function capital F of z inverse e to the power x, and if I want to take this, then this is going to be f dash e to the power x over z square minus, and if you want to take ddx of f of z inverse e to the power x, then this is just going to be f dash, right? This is just chain rule of differentiation. You're going to have e to the power x over z, and if you compare this and this, then you realize ddx of minus 1 over z minus 1 over z ddx of z inverse e to the power x is actually minus z square, which is ddz of e to the f z inverse e to the power x. Good. So now that we are here, and the reason is, see, I want to convert the derivative with respect to z to a derivative with respect to x, and there is an ulterior motive for that, because I know here the integral is with respect to x, and if I replace this derivative with respect to z to a derivative with respect to x, I can use integration by parts. I can make my life a little bit more simpler. So I have ddz of f plus m of z as 1 over m minus 1 factorial 0 to infinity ddx x to the power m minus 1, and then I had a ddz, which I can see that is going to be minus 1 over z minus 1 over z ddx of z inverse e to the power x minus 1. So that this is minus 1 over z 1 over m minus 1 factorial 0 to infinity dx x to the power m minus 1 ddx of z inverse e to the power x minus 1. Now let's integrate by parts. When I integrate by parts, I have minus 1 by z m minus 1 factorial, and now in this case I take this one as the first function, so that I have dx of this, so that gives me z inverse e to the power minus of this times x to the power m minus 1 minus integral dx m minus 1 x to the power m minus 2 over z inverse e to the power x minus 1. The limits are 0 to infinity. This one vanishes in both the limits, so that I have 1 by z, this minus and this minus makes it a plus, m minus 1 factorial d 0 to infinity. I have m minus 1 in the numerator, that comes from this dx x to the power m minus 2 divided by z inverse e to the power x minus 1, and this is 1 over m minus 2 factorial 0 to infinity dx x to the power m minus 2 z inverse e to the power x minus 1, which surprisingly is f plus m minus 1 of z, so that I have z of f plus m minus 1 I have f plus m minus 1 of z ddz of f plus m of z. Therefore, this implies that ddz of f plus 5 by 2z is going to be 1 by z f plus 3 by 2z, and ddz of f plus 3 half of z is going to be 1 by z f plus half of z. Correct? Now ddt of f plus 5 half of z is going to be ddz of f plus 5 half of z times dz dt. And similarly, d dt of f plus 3 half of z is going to be df plus 3 half of z dz dz dt, right?